This conference will now be recorded.
So good evening. So we are studying refraction at spherical surfaces and refraction by lenses. So in the last class, if you remember, we had derived the equation relates the image distance, object distance, refractive indices of two mediums, and the radius of curvature of spherical surfaces. So this we had derived, and you can see this relation we had got like this n2. So in this case, I'll just make you remind little bit. Let me just recapitulate what is happening over here. So this is refraction at spherical surface. Suppose you have two transparent medium, and the interface between the transparent medium, transparent mediums having refractive indices n1 and n2 is the spherical one. So the interface is spherical one. So when light refracts from one medium to another medium, so in this case we have taken that the light is refracting from rarer medium to denser medium. So in this case we have just considered n2 is greater than n1. So n2, this medium actually denser medium we had taken, and this was rarer medium. And see, v is the image distance and u is the object distance. So here a point object O has been taken, and the light is coming from this point object and getting refracted by this spherical surfaces, and using the geometry and certain approximations, mainly paraxial approximations and small aperture approximations, we had derived this equation. So n2 by v minus n1 by u is equal to n2 minus n1 by r. R is the radius of curvature of this spherical interface. Okay, so this is what we have derived, and the details we had discussed in the last class. So why I'm recapitulating this, because we need this concept to learn or to derive the lens maker's formula or refraction by lens. Okay, so lens maker's formula is actually related to formation of image by lens. So we'll just see that, and today we'll take up what is combination, like how the power changes in combination, or the focal length changes in combination of many lenses. So those things we'll be learning today. So see, this is refraction by lens, and from here we'll be deriving lens maker's formula. Lens maker's formula. Okay, so see, in the previous class we had discussed refraction at spherical surface, and in that case only one spherical surface was there like this, right? One spherical surface was there, but we have now two spherical surfaces which is making a lens. Okay, so then in this case how do we use that knowledge the knowledge we have for a single spherical surface to derive an equation which will relate the object distance, image distance, and the radius of curvature, the radii of curvature for these two spherical surfaces. We'll see now. So we have to keep in mind this particular formula n2 by v. V is the image distance, u is the object distance. Okay, these are the things we have to remember. That formula we have to remember a little bit, and using that we'll be able to derive the equation or the formula for like lens maker's formula. Okay, so see, in this case, when we have two spherical surfaces in lens, and obviously the approximation is thin lens, okay, thin lens, and in this case, see, there are two spherical surfaces A, B, C, and another one is A, D, C. These are two spherical surfaces. That is making a lens in combination. So obviously you can get an idea that there will be refraction twice. Once at this ABC like spherical surface, and another one this ADC interface. This also will cause the refraction of light. So I have two spherical surfaces, so there will be refraction twice. Okay, so so image formation by lens can be actually thought of two-step process. It can be thought of two-step process. So this is one step. So what is the first step? See, you have ABC surface. So what will happen? First, light will come and refract at this ABC interface. Okay, and it will create a real image where at this particular point, suppose this is, see, from the center, let us take this is V1. Okay, the distance is V1. Okay, so this lens, this ABC surface will create a real and point image of this O at this particular point I1. So I1 is the point image of this object O, and this is happening out of refraction at the first surface ABC. So Deepa has come now. Deepa, see, I'll just quickly in 1 minute I'll just recap what I have done. See, I just had written this thing, refraction at spherical surface. So in the previous class we have learned this. Today what we are going to do, we are going to derive lens maker's formula and consequences of all those things like thin lenses, combination of lenses, power, etc. we'll be learning today. So when we talk about image formation by refraction at single spherical surface, this is what the formula we had derived last day. Okay, and we had taken that, see, this, there are two medium N1 having refractive indices N1 and N2, and we had just assumed that the N1, so this medium is rarer medium, and light was like object was at rarer medium, and the image is forming in the denser medium. So that is what we had thought, and then we have derived this formula. Now we are going to see how lens is helping us to get an image, or how image is formed by a lens or by refraction of lens. So in this case, look, you have two surfaces ABC and ADC. See, ABC, one spherical surface, maybe having radius of curvature R1, and ADC, this is the opposite side, so it has suppose the radius of curvature R2 with a minus sign. So since there are two spherical surfaces, there will be refraction twice for a light. Suppose a light is going from O, point object O from here. So it will refract at ABC first, and then further it will refract at ADC also, and then final image will be formed. So to analyze this or derive this lens maker's formula, which relates the radius of curvature, refractive indices, and image distance and object distance in the, and also the focal length. So to derive that equation or that formula, we can think the image formation is happening in this lens by two-step process. Two-step process. So what is the first step? We'll be thinking that the light is coming from this point object O. It is getting refracted by ABC surface first, and it is producing an image. This is, in fact, this is actually real image. Where it is producing is like it is actually produced in the medium 2 having refractive index n2. It is produced in the medium 2. That is what we have to think. Okay, and this particular image will be acting as the virtual source. See, this particular image which was formed by ABC surface will be acting as virtual source. Virtual source for ADC spherical surface. Okay. Now, upon refraction at this surface, ADC, the light will be converging here or meeting the principal axis at this point I, and you will get the final image in the medium 1 having refractive index n1. Okay, so this will be the final image. So you can see this is the intermediate step. Excuse me. So I hope you have understood this. Now we'll go to the mathematical part. See, I'll just repeat this once again. When we are studying the formation of image by lens, it has two surfaces. So light will be refracted twice. So it can be thought of two-step process. In the first step, AB surface, so refraction will happen at AB surface, where a real image will be formed at I1. So let us say the image distance is V1 from the optical center of the lens. Okay, and this is real image, and real image is formed actually in N2. This you have to just note this point. This is important. So this image is formed in the medium 2. Okay, and what is the second step? So in the second step, you can see this I1, the real image which was formed by the refraction at ABC, will act as the virtual source or virtual object or source it will act as virtual object for the ADC surface. And at this, after refraction at this ADC surface, finally light will meet the principal axis at I, and this will be giving you the real image or the final image for the object, point object O. So this I will be the final image. Suppose this final image has image distance from the optical center V. So now what we'll do, see, we have already learnt this formula, refraction upon refraction at spherical surface. So this formula we have obtained. So we'll be using these formulas for these two surfaces. So if I write that particular formula, so for this ABC, like refraction at ABC spherical surface, where the light is coming from N1 and the image is formed at N2, like in the N2 medium 2, and suppose this image distance is V and object distance is U. Okay, so what we can write from here, we can write N2 by, this is V1, suppose V1 minus N1 by U is equal to N2 minus N1 by, see, the radius of curvature is R1. So this is equation number 1. Similarly, if we write the same formula for ADC surface, so what will be that? This, see, we have to see, this is actually the medium where, so refractive index, this one we have to write medium where the image has been formed. So in this case, the final image is formed actually in the medium 1 having refractive index N1. So N1 by V, suppose this is the final image and distance is V. So N1 by V, then minus object was where, see, in this medium N2 by V1 was the object distance for this. See, V1, this is the object distance, virtual object distance V1. Okay, now look, here we have to write N2 minus N1, okay, by, see, the radius of curvature is actually taken this way, isn't it? So this will be minus R2. Okay, so if we rewrite this, what we get, N1 minus divided by V minus N2 by V1 is equal to N1 minus N2 over R2. This is equation number 2. Okay, now if I add these two equations, see, you can add these two equations and get the final simplified formula. See, if I add these two equations, let me see whether I have, okay, so adding these two equations, what we get, see, if I add this to left hand side, I'll add, look, N1 by V, okay, N1 by V, this will be here N1 by V, then N minus N2 by V, and here see plus N2 by V. So these two will cancel each other. Okay, so you will get finally minus N. Okay, so N1 by V. Okay, so this will be N1 by U. So left hand side, if you add, you will get N1 by V over, see, N1 over V minus N1 over U, and the right hand side, look, you will get, see, this N1 minus N2 you take common, so this minus, okay, I can just give the name here itself. So if we add this right hand sides, what you get is n2 minus n1 whole into 1 by r1 minus 1 by r2. Okay, so this is what you will get. I'll just write in like freshly whatever I have got after doing the simplification, adding the two equations, what I get. See, I get n1 common, 1 by v over 1 by u is equal to n2 minus n1 whole into 1 by r minus 1 by r, r1 minus 1 by r2. Okay, so this is the formula I have got. So I'll just do a little bit more simplification, and this is actually for the thin lenses. Okay, so these are applicable. So this formula particularly will be applicable for thin lenses, whether it is concave or convex, doesn't matter. Now see, I'll just do a little bit more here. 1 by v minus 1 by u, and let us write this is n2 minus n1 over n1. Okay, and this as it is. Okay, so look, in this case, if we keep the object at infinity, if we keep the object at infinity for a lens, if we keep the object at infinity, so the parallel rays which are coming after refraction, where they meet at the focus. Okay, obviously the lenses has lens has two focus. One is this one, and this is f2. So the focus, principal focus, which is in the like near the object or in the side of object, is called as first principal focus, and the other one, this one, is called second principal focus, but they are equidistant from the optical center. So if you keep your object at infinity, that means u infinity, then rays will be parallel. After refraction, they will meet at the focus. Okay, they'll meet at the focus. So the focal length, so this v will be then f itself. Okay, so if your u is infinity, that means you place your object at infinity, then the object image distance or the image will form at the principal focus, so which has focal length small f. Then I can just replace upon after having this approximation, we can just rewrite the formula. Look, I can write 1 over c v, I'll replace with f, and this will be 1 by infinity means 0, and see here I can write n2 over n1, that I can write as n2 1, and here it is minus 1, and along with that this will be 1 by r1 minus 1 by r2. Okay, so 1 over f will be finally n2 1 minus 1. So this is the refractive index, relative refractive index of the medium 2 with respect to 1. Okay, all right. So this is the formula which is called as lens maker's formula. What is this called? Lens maker's formula. I'll just, okay, let me clean and rewrite what is lens maker's formula. So finally what we get is lens maker's formula. See, lens maker's formula is given by 1 by f is equal to n2 1 minus, okay, I'll just write it elaborately, n2 minus n1 over n1 into 1 by r1 minus 1 by r2. So r1 and r2, as you know, the radius of curvature for the surfaces. Now look, if my n1 is air, okay, if this the first medium is air, okay, or rarer medium is air, then n1 will be 1, and suppose n2 is n itself. So then I can rewrite this formula as n minus 1 into 1 over r1 minus 1 over r2. This is our actually very known formula. Like this is the known form of Lensmaker's formula. So this is the known form, and this is the general form. This is general form, and this is for air to glass or air to any medium. Okay. So this is called Lensmaker's formula. Why is it called Lensmaker's formula? Because if we want to make a lens of our desired focal length, if we know the refractive index of the material being used for making the lens, we can just have suitable radius of curvature to get this particular wavelength. Okay, sorry, focal length. So we can just choose the see this radius of curvatures. Okay, radius of curvatures, and then we can get the desired focal length. So this is what called Lensmaker's formula. So in this process, see, I'll just write this Lensmaker's formula down here. 1 by r1 minus 1 by r2. Okay. Now see, we have done one approximation. 1 by, see, if we write this 1 by v minus 1 by u is equal to 1 by f. So this is for a thin lens, and this is called actually the equation of lens, or equation for lens, thin lens. Okay, equation or formula for thin lens. Okay, equation for thin lens. So this equation we already know, and this is very important to solve various numerical problems. Okay, so these two formula you have to remember properly. Okay, now see, we can use this formula to solve an important problem and frequently asked in various competitive exam. Let us take one of them. See, okay, before I go to that problem, I'll just tell you few things over this Lensmaker's formula. This formula is actually applicable for convex. We have already derived for convex, but it can be applicable for concave as well. We have derived for real image, but it can be used for real or virtual both images. Okay. Okay. So this is universally applicable. Now look what we are going to do. We are just trying to find out what will be. See, suppose, okay, let me just state the problem itself first. This lens equation, you know, I'll just erase this so that I get some space over here. Okay. See, you have one lens over here, equiconvex lens. I have defined in the previous class what is equiconvex lens. You have two surfaces, spherical surfaces having same radius of curvature. So r1 is equal to r2 is equal to r. So this is equiconvex lens. Now if you cut this equiconvex lens into two halves, okay, and use one half of the lens, okay, then what will be the focal length, what will be the focal length of this particular half or each half. Okay, so you have got two halves now, two halves. So what will be the refractive, sorry, the focal length of both halves, like each halves. Okay, so see, we can use this length makers formula to find out this. As it is equiconvex, so both are R, but see, R1 will be positive R and R2 will be actually negative R. Okay, all right. So in the length makers formula, if we apply this, R2 is, see, R2 is minus R, then what we get from there? Let me first get there. So n minus 1, 1 by R plus 1 by R. Okay, so this is what we get for equiconvex lengths. So we get 2n minus 1 divided by R. Okay, so this is what we get. Now see what happens if we just cut it down. See, we'll get a plano-convex lens. That means one plane having radius of curvature tending to infinity, another one has radius of curvature r. So look, if I just put this here, okay, if we just put it here, what we get? Let us see what we get in this formula. If we put that, see, focal length, suppose I get for this left half, so R2 will be minus infinity. R2 will be minus infinity. Okay, so for that case you get n minus 1 over R. Okay, you get n minus 1 over R, and suppose this is refractive index, sorry, the focal length, suppose it is f prime. Okay, you get f prime. So what is f prime? You look here, what is f prime? F prime is actually, okay, so I'm sorry, this is a 1 over up, 1 over f. I'm sorry, so this will be 1 over f is equal to this. So I'll just erase this part to finally write the form, like what you get. So this was 1 by f originally when the equiconvex lens was there. So this was 2n minus 1, 1 over that. Okay, 1 over f is equal to this. Now what we get? 1 over f prime, we get n minus 1 by r. Okay, so look, in this case what we are getting is, see, n, so if I just put this value, what I get? 1 over 2f. So 1 by f prime is 1 over 2f. If we just erase this part and write, let me write this, what we get finally. See, what we get, f prime is equal to 2f. Do you agree with me? So do you get, I hope you know this, but you may not know how to get f prime is equal to 2f. So each half will be having focal length twice of the original focal length. Okay, so after making half in this way, after making half in this way, you will get 2f. Okay, but if you make half like this, what will be the change? If you just cut it here, like this, horizontally, you have this portion now, and another half is like this. Okay, so in this case actually f prime will be equal to f only. Okay, both the surfaces are there always, so you won't have any change in that case for the focal length. Okay, so students, you have, I think, yeah, Deepa, I hope you have understood this. Okay, if not, you can ask me now, or otherwise I'll go to the next topic. Is this okay? Have you understood this? Okay, Deepa, I'll just go to next section then.
Yes, sir.
Okay, now we'll see. Okay, now we'll see there are few like formula or principle for the image formation by lens. See, if I take a convex lens, the principle in the sense like how the refracted rays will behave. Suppose I have an object of h height. Look, if the is ray which is parallel to principal axis is getting refracted, it will be actually going through the focus after refraction. Second focus, obviously you can say that this is second focus or principal focus, second principal focus. Okay, if any ray is passing through or coming from focus and getting refracted, after refraction the ray will be parallel to the principal axis. So this is the one, and this is the parallel ray, parallel incident ray getting refracted and meeting at the principal axis, like meeting the principal axis at focus. And if you take any ray which is passing through the center, optical center of the lens, it will just pass through. There will be no bending of that ray. Okay, and and wherever at least two rays are meeting, there will be image forming for that particular object. Okay, so this is the image formation by convex lens. And in case of this is convex lens, convex. And now we'll see how the rules are for concave lens. So in case of concave lens, you see the ray which is parallel to the principal axis, upon refraction it will be seeming like getting diverged from the principal focus. Okay, from the principal focus. And if any ray passing through the optical center, obviously that will go undeviated. Okay, it will pass through the lens without any deviation. Okay, so then if you just retrace or trace back this particular ray, see with the dotted line, it is actually meeting here or intersecting the second ray over here. So in this case, you look, you will have this ray, this image, and this image is actually virtual image. This image is actually virtual image because the rays are not really meeting. You have to trace back to make the light meet over here. So this kind of images are called virtual image, and in this case this is real image. When two rays are really meeting, so there will be real image formed. And if the two rays, refracted rays, are not really meeting but appears to meet, or if you retrace them back, then they will meet. So for that case, virtual image will be formed. And These virtual images cannot be seen in screen. You have to see this is actually, this cannot be seen in screen. Okay, all right. So these are the principles of image formation by lens. Now one more point we have to discuss over here, what is called magnification. This is obviously called lateral magnification. Magnification, even it can be called as lateral magnification also. What is magnification? Magnification is actually defined as the ratio of the image formed, image like height of the image to the height of the object. This is object height and this is the height of the image height of the image. So if you get a number which is greater than 1, that means the size of the image is greater than the object. So this will be called magnified image then. Magnified. Okay, this is called a magnified image. And see, this magnification can be written in terms of the ratio of image distance to the object distance, v by u. So with this ratio also magnification can be expressed. Now look, magnification, when the magnification, see what is the importance of the sign of the magnification. Actually by seeing the sign, whether it is positive or negative, because it is the ratio of v by u. Now depending on the sign of v or u, m can be positive, m can be positive or negative. Okay, it can be positive, negative value, or it can have even zero value. That means when you don't have, sorry, not zero, you can have maximum, minimum 1 and maximum can be depend. Okay, so you can have minimum value, sorry, I think it is not true, minimum maximum, that depends on your v by u. So you can just control it by v by u as well. Okay, okay. So now see, I'll just talk about positive or negative sign. When you have positive sign, then what is the nature of the image? It will be real. Okay, then diminished. Okay, real image diminished in size. And what else? With the positive sign, yeah, these are the main thing. And obviously this image will be inverted image with positive sign. When, oh okay, so yeah, I'm sorry, this is actually other way. This is when it is negative, then these are the things: real image, diminished and inverted. When you have positive, then you have virtual image, then it will be magnified. That means this ratio will be greater than 1, magnified. And also it will not be inverted, it will be actually erected image, erect image. Okay, erect. So these are the nature. You have to see, sometimes there will be a numerical problem, and then they will ask, like, what are the nature, where is the position of the image, whether it is real or virtual, whether it is diminished or magnified, whether it is inverted or erect. So these are the things you can get from this sign of the magnification. Okay, all right. So now we'll learn what is power of a lens. What is power of a lens? The power of a lens is defined as the tangent of the angle by which it converges or diverges a light falling at unit distance from optical center of the lens. Okay, this is the definition of the power of lens, and I have borrowed from ncert textbook, as I do always. I follow that book as main reference for the lectures. And here, before I discuss this definition of the power of the lens, let me tell you what is power. Actually, power is the measure of how much light will be getting bent by a particular lens. Okay, so because of this power, lens can diverge or converge the incident ray or refracted ray. Okay, so the ray can be converged or diverged by lens, and at what distance it will be converged or diverged, that depends on the power. If the power is denoted by P, if the power is, so when the, see, if I take, for example, if I take a convex lens where the light is getting converged, that is called principal focus, and focal length is f. Okay, if my P is more, suppose I'm just taking two cases, like in one case P1 power, and another lens the power is P2. If suppose P1 is greater than P2, then see, P1 will converge the light before, in a shorter length, shorter focal length. So when your P2 is more, then what will be less? So sorry, P1 is more than P2, then look, F1 will be less than F2. Focal length will be less than the other one. Okay, that means the focal length, sorry, the power is, see, power of a lens is defined as the tangent. See, mathematically we can define by tangent of the angle by which, see, this is the original direction of the light, but it is bent by this much angle, or it is converged by this much angle. So if we take the tangent of this angle, then we get power. So power, but in this case, see, if I just take the tangent, in this case, suppose this is H is the, like, the ray which is meeting, like, getting incident at that particular height from the optical center is H. But so this is actually tan delta from this particular figure. But power is, like, this can be, this tan delta can be told as power if the ray is meeting the lens at unit distance, that means H is equal to 1, then it will be power. So 1 over F. So if H is equal to 1, then this tangent can be tangent of the angle by which the ray is getting converged or diverged. Then that tangent of that angle will be the power. So you can see, if H is 1, so in the definition itself it is written, see, it converges or diverges a light falling at unit distance from the optical center of the lens. Suppose here the light is coming and falling, so this is the H height, and this height has to be unity. Okay, then only this definition, this tangent angle of like tangent of this angle delta can be told as power. So what we have got, power is equal to tan delta when you have H is equal to 1 over F. So this is the, okay, this is the power. So this is your power. So P is actually, power is defined as reciprocal of the focal length also. So this is the power. Definition of power is reciprocal of the focal length. So sometime you will be given focal length, suppose 5 centimeter, then you have to find out what is the power of the lens. Okay, obviously before we do this problem, let us go through this like unit of the power. See, unit of power is defined like unit of SI unit of power is diopter. Okay, diopter. So it is per meter. Okay, it is actually per meter. Diopter means per meter. Per meter. Diopter unit, one diopter is per meter. Okay, 1 over meter or per meter. Diopter is the power of a lens whose principal focal length is 1 meter. Okay, one diopter is the power of a lens whose principal focal length is 1 meter. So meter inverse is called as 1 diopter. Suppose here in this case centimeter is given. So I know power is 1, see, 1 over f, then I have to write diopter, right? If the focal length is given in terms of centimeter, then you have to write 100 over focal length in centimeter. So this you have to write in centimeter. Then you get diopter. Okay. So in this case, what is the power? 100 over 5. That means 20 diopter, and it is written by like capital D. Power is 20 diopter. Now in this case, you look, when the focal length is positive, then the power will be positive. So focal length will be positive for convex lens, and it will be, this is convex lens, and focal length is negative 1 for concave lens. So power will be positive for convex lens and negative for concave lens. Okay. So Deepa, I think I'll just stop it here for today, or I have got another 5 minutes. If you have patience, then I'll complete this combination of lens. But in that case, it will go more than 5 minutes. So I'll just stop it here. Combination of thin lenses and combination of thick lenses, etc. I'll be discussing in Wednesday's class. Okay, in the next class. So today I'll stop it here. If you have any doubt or any question or query, you can ask me now. Deepa, you can ask me if you have any query or questions. So combination of lenses I'll just take up in the next class. That day I'll be discussing combination of both thin lenses and thick lenses also. So what's up, Deep? Yeah, Deepa, are you able to hear me? I'm not getting any response from your side. Okay, so I'll just stop it here. We'll meet again on Wednesday for this class. So ray optics, I think we'll have 2 more classes maybe with numerical problems, and I think, yeah, 2 more classes, then we'll stop geometrical, like we'll finish the geometrical optics, and next we'll go for wave optics. Okay. Okay, bye.
Thank you.